If you've looked ahead, you'll notice that chemical kinetics comes first, and then equilibrium comes after that. It seems counterintuitive, but in fact, an understanding of chemical kinetics, or the rates of reaction, actually help understanding of equilibrium. And of course, that may not be obvious until we get to chapter 13 and look at equilibrium. But in order to express a reaction rate, and you can look at chemical reactions. Well, I better not introduce that topic yet. Let's just focus on reaction rates. How do we express the rates of reaction? Well, actually, when you consider a chemical reaction, you got reactants and products, so you could identify the rate of reaction in terms of disappearance of reactants or appearance of products. But either way, it's simply the concentration of whatever component you choose at the later time, at the final time. Sometimes we write it this way. So the concentration of A at time t. Let's see. At final time minus concentration of A at initial time. So that's typical in calculations in chemistry and physics, for that matter, is you always take the final minus the initial. So sometimes that may give you a negative value. And if you're looking at disappearance of A, then this one would be smaller than that one, and you would get a negative value. And then divided by how long does it take? Well, let's see, let me be consistent. Final minus initial. So this is concentration, and we can express it that way. Square brackets means concentration. So it's a change in concentration that occurs in that time interval. Okay, another way to write that is just a change in A divided by change in T time. That's what the delta means. It's just a change. Typically, A is expressed in molarity, or moles per liter. But sometimes, especially when we're working with reactions with gases, we'll use partial pressures of the reactants. Remember Dalton's law of partial pressures, right? The total pressure is the sum of the partial pressures of each of the gases that make up the total. So you can look at the partial pressure of, and that might be in atmospheres, it could be in pascals, it could be in millimeters of mercury, or it could be, what's another one? Torr. Any one of those will do. And if you use the same unit of measure for all the pressures in the reaction, then it doesn't matter which one you use. But when in doubt, unless it says pressure, assume that it's molarity. And this is often used for gases too. You can speak of gases in terms of moles of gas per liter of gas. Okay. So that's an expression of reaction rate. And that's typically the way it's presented, just like that. Rate equals change in A divided by change in time. Now, for this reaction, everything is gaseous. Right? Nitrogen dioxide yields nitrogen monoxide plus oxygen. And if you look at the concentrations as you proceed, notice at time 0, you're starting out with 0.01 molar nitrogen dioxide and no products. So the change, the instantaneous change that occurs at the very beginning of the reaction is called initial rate. And that's often the time it's best to investigate a reaction. Why? Because when you have this reaction, that arrow actually should be a double bar, one going one way, one going return. Because you can get return reactions, these two can recombine and make that. So if you do it, if you measure the rate down here somewhere, there's a possibility that you're getting return rate too. But this is data collected for this particular reaction over time. And notice as NO2 decreases, NO and O2 increase. Right? And see the ratio, 0.0011, 0.0021. It's 1-to-2 ratio, all the way down. Should be all the way down. Yeah. Okay. And as this one disappears, and I assume we've got a reaction here where the return reaction is very slow. It's not significant. Otherwise, you should see a leveling off of these amounts, and you don't. So in this case, the reaction doesn't have a significant return rate. Let's see. So what happened here? Between here and here, you get a difference of 0.01 and 0.0079. So that's 1, 2. So that's the change in concentration. Well, change in NO2, in O2 is that concentration. These are all in molarity. So notice the change here, 0.021 showed up. The ratio here is 2-to-2 or 1-to-1. So what disappeared here showed up over here. So the stoichiometry is correct. But we can express this reaction rate in terms of any one of these components, either the appearance of these or the disappearance of that one. So this is what you're going to see, and this is out of your textbook, I'm pretty sure. That's going to be hard. That's not going to pick up very well on the video. But it is a reproduction of a graph from your textbook. And you'll notice that you've got 3 components here. And over time, their concentrations change. Okay? So as NO2 decreases, NO and O2 increase. And you reach a point. Well, we haven't reached a point yet. We've only gone out 400 seconds. So in that amount of time, you get a decrease in NO2 and an increase in the other 2 components. And the rate, how do you do a rate on this? Rate would be the change in concentration divided by the change in time. That's a slope, correct? Rise over run. Change in y divided by change in x. So how do you do it on a curve? Well, you need something called instantaneous rate. This is a concept that you pick up in calculus. The rate at any one point along this curve is equal to the slope of a line that's tangent to that curve. So it only touches in one point. Remember that concept in math. Tangent touches a curve in one spot. Right? So we can draw a straight line that only touches right there. So at that point, the slope is this. What would it be down here? Well, it would be a different slope, correct? So at any one point in that that curve, for the disappearance of NO2, the rate's going to be different. So it depends on where you measure as to what the rate is. I accidentally punched that. Now, if the curve is very shallow, then the tangent approaches the slope of the curve, or the curve approaches the slope of the line. Okay, so that's the concept of instantaneous rate. Wherever the tangent touches that line, the slope of that straight line is the slope of that curve at that particular point. All right, so when we've got this equation, we're going to express this particular equation rate in terms of disappearance of NO2. So we have the concentration of NO2, and the rate, we had, let's put them both up here at the same time, right? Our initial rate, concentration, let's write it in terms of this one, there, over time. Change in time, change in concentration. But for any reaction, the rate law, this is the reaction rate. The rate law says that the rate is equal to some constant value times the concentration at any time to some power. Okay? That's known as the rate constant. And this is the order of that particular reactant. The order, when you hear order, think powers up. The power of the concentration of NO2. It could be 0. It could be 1. It could be 2. It could be 3. Actually, I've seen fractional orders. But we're going to try to keep it simple and use whole numbers wherever possible. It's easier to study in the beginning if you use whole number powers. In fact, if you have a fractional n, not a whole number, it's very likely that you've got some undiscovered component in here that hadn't been accounted for. Usually, if you've accounted for all your components and all the variables, then this is going to be a whole number. Okay. So why don't the concentrations of the products appear in the rate law? Well, it's the initial rates idea. We're studying this reaction at the very beginning. So the initial rate is the rate law for this reaction. And that occurs when the reverse reaction is insignificant. It's at the very beginning of the reaction. It's also important to recognize that this value, this order, has to be experimentally determined. You cannot derive it from the balanced equation. Okay. So that's going to be the $64,000 question in any reaction is what's its order, and you have to use the actual data from an experiment to determine the order. I'll leave that up there. Okay. So there are a couple of different ways to express rate laws, and it depends. One is useful under certain circumstances, and the other is more useful under other circumstances. And this goes back to calculus, right? But you don't have to know calculus to understand this. Differential rate law. this simply shows how the rate of the reaction depends upon the concentrations of the reactant. And this is the differential form. That's the differential rate law. The integrated rate law incorporates information about time dependence, right? See, we've got no time in here. In fact, the time is embedded in the rate constant. The values for time is embedded here. This is concentration only. This incorporates the time. But once you know this, it doesn't allow for variability. You can't vary the time. But with the the integrated rate law, we can incorporate time dependence. In other words, we can allow time to change with that law. All right. But the differential integral relationship depends on what type of reaction it is, what the order of the reaction is. Right. We're going to look at examples in just a minute. So what this statement says is, if you know one, you can deduce the other. So sometimes it's more convenient to determine the integrated rate law. And from that, you can write the differential rate law and vice versa. So they are related in well-defined ways. And we're going to look at those in just a second. Very often, how convenient one is versus the other determines which one you're going to investigate, which one you're going to derive from an experiment. Now, why do we need to know the rate of reaction? There are a number of reasons, but primarily, we want to know what occurs during a reaction. In other words, when we write this reaction, what was it? NO2 yields NO plus O2, and those are all gases, like that. When we write that reaction, that's the overall reaction. In other words, there's something going on between here and here that usually takes 2 or more steps to accomplish. That's called the mechanism. This does not tell you the mechanism of the reaction, but if you understand the kinetics of a reaction, sometimes you can tease out individual steps of the reaction, and you can propose a model of the reaction mechanism. All right, we're going to do that too. All right. This is the method of initial rates. And in order to do the method of initial rates, you're going to have 2 or more experiments, separate experiments. And then you're going to use the information from those experiments combined in whatever way you choose to determine the either the differential or the integral rate law. All right. So let's talk about orders again. Remember, I said order is, think of power. And that's where it's always placed. Suppose we have a reaction that doesn't have one reactant, but maybe it has 2 reactants. If it has 2 reactants, then each reactant has its own order. And that has to be experimentally determined. Well, so if it only has one rate constant. And by the way, this is a differential rate law right here. This reaction rate constant is multiplied by the concentrations of each of the components, and each of those components has its own order. So this A order is N, and this B order is M. And you can say the order of reaction with reference to A is 1, 2, whatever, 3, 0. And the reaction with reference to B is 0, 1, or 2. But if you discuss the entire reaction, the overall order is simply the summation of the two. So the overall order would be this one plus that one. Okay? All right, just to be sure this rule sunk in, how do exponents or orders in the rate laws compare to coefficients in a balanced equation? They don't. They have no relationship whatsoever. If they look like they do, it's purely coincidental. They are unrelated. The balanced chemical equation is an expression of stoichiometry. That's overall reaction. Now we're going to find out later that once you know the mechanism of a reaction, the individual steps that are buried in that arrow, then you can say something using the coefficients of the individual steps about the order. But that doesn't come yet. We've got, when you're looking at the overall equation, then it's experimentally determined order. Has nothing to do with the overall reaction coefficients. All right, so we're going to look at 3 different orders of reaction with reference to only a single reactant. We're going to try to keep it simple. This is the 0 order. Let's see. Yeah, I guess I'll just write this. So the 0 order is written like this. It's rate equals some reaction rate constant times the concentration of whatever A happens to be to the 0 order. So what does that mean? That means the rate is actually has nothing to do with the concentration of A. Right? Because anything to the 0 power is 1. So rate is actually equal to the rate constant. All right, this is the differential rate law. The integrated rate law is the concentration of A at any time t during the reaction is equal to negative K times the amount of time in the interval plus the initial concentration of A. Right. So for this integrated rate law, the initial concentration of A does matter, and the final concentration does matter, and the amount of time. And these K's are equal. That's the same K as this K. All right. Now, the advantage to writing this integrated rate law, look at it. Right? Straight line. That's Y. This is the slope. This is T. And this is the Y-intercept. So writing that, the integrated rate law this way gives you a straight line relationship. And for scientists, that is superior to any curve. I mean, the curve may represent reality under circumstances. But when you're trying to extract information from an experiment, a straight line is preferable because it's so well defined. So this is what it would look like if you graph is with X would be T down here, and concentration of A here, right? So A0 is right here. At time 0, A would be up here, right? How do I know that? Because negative K is negative slope. So it's going to slope like that. A is going to decrease over time, which makes sense. Because A is a reactant and it should disappear with time. So the slope here is equal to negative K. So if you plot data, time versus concentration, and it gives you a straight line, you know that it's 0 order. Right? That's a dead giveaway. If you end up with a negative slope, plotting time and concentration of A with no transformations whatsoever, just the raw data, then you know you have 0 order. Okay, there's one other bit of information we can derive, and that is the half-life of the reaction. Okay. You may have heard of half-lives in terms of radioactivity. Half-life of uranium-235 is like, I don't know, 1.5 million years. Or some other isotopes, the half-life is like 20 milliseconds. So it varies. So what does half-life mean? Half-life means the amount of time it takes for half of the reactant to disappear. So we write that as T1/2. Right? We do need to know the initial concentration, and then we need to know the K times 2. So this is the same K here, as here, as here, as here. So what does this say? If we start off with the concentration here, as the concentration increases, the half-life increases, right? Because they're directly proportional. Here is directly proportional. As this one gets bigger, that one has to get bigger. But if K gets bigger, then half-life gets smaller. So a large K here means a small half-life. All right, so that's 0 order. You probably guessed the next one that comes. First order. So in this one, rate equals K times the concentration of A. And there's a 1 up there. We don't write the 1. And you really don't need to write this one. Because if you write rate equals K, you know it's a 0 order. So this is the differential rate law, the integrated rate law. We make a transformation. If we transform the concentration of A to the natural log of A, then we get another straight line. Instead of doing this, we say the natural log of the concentration of A equals negative K times T plus the natural log of A0. Okay, so what does that mean? Well, it's a straight line form. That's typically how you see the integrated rate law, mimicking some straight line. So this is Y, this is B, this is slope, and that's X. So if we plot it, we need to plot it on a log format, like that, versus time. And if we do that, notice we get a negative slope again. But the slope this time, well, the slope this time is equal to negative K. But it has to be this transformation, the natural log. And you got a key on your calculator that says LN. You also have one that says log. This is natural log, which is the base E. Log is base 10. Right, so don't get those two confused. And then this one also has a half-life. Right? And the half-life of this one, well, after we plot it, so there's a natural log. This is a different reaction. And if you plot those values, right, less and less and less as you get down, like negatives get bigger this way. So you have to be sure you orient correctly. And then time, then you get a negative log. And the T1/2 in this case is 0.693 divided by K. So notice here that while the integrated rate law does take into account concentrations and time, the half-life is only interested in the K. It doesn't care. The half-life never changes no matter what the concentration is. The initial concentration doesn't matter for a first order reaction. So sometimes it's more convenient to use this one, right? If you can determine the half-life of your reaction, then all you have to do is set it here and you can find K. But you've got to be sure that you got a first order reaction. So the first order of business is to make the transformation, plot it like this. If it's not a straight line, then it's not zero order. If it's a curve, it's not zero order. If it's a straight line with natural log, then it's first order, and you can take advantage of that relationship. Right? We'll have problems to solve that will use that relationship. Okay. That's first order. Now we're going to do one more, second order. Let's write it in English. Right? So, probably guessed what this one will be. K squared. Okay? Now, if it hasn't occurred to you yet, you may wonder, well, what do you do if your reaction has two reactants in it? If it has an A and a B? Well, we're going to do, that's our kinetics lab. We're going to have a reaction that has two components in it. So how do you deal with determining whether it's zero first or second order in one particular reactant? Well, the trick is you make one of the reactants so high in concentration that it effectively doesn't change during the reaction. And you incorporate that B term into the K. And now you only have this one to deal with. But that's not the same K as the reaction with both components. That's a pseudo K. So we give it K prime. That's just a taste of what's coming. How you deal with a two-component reaction when you're only identifying single components for zero, first, and second order. We're going to digress for a minute. First order reaction, 35% complete at the end of 55 minutes. What's the value of K? Okay, you're told that it's first order, and you're saying the reaction is 35% complete at the end of 55 minutes. All right, so what does that look like? I like to draw a table. So if you have concentration of A, and then you have time over here, well, if you start out at some value here, X, and this is time 0, then after 55 minutes, it's 35% complete, which means 35% of X has been used up. right? So what's left over? Well, 65%, right? We'll use fractional equivalence. 0.65x is left over after that amount of time. So, this takes a good bit of math. Sorry. If we start from the integrated rate law and we solve for the ratio of A to A0. So this is A0. And this is A. Up there, 0. And this is A after 55 minutes. Okay. Then if we solve this equation for the ratio of A to A0, then we can say something about completion, right? It's a ratio of one to the other, completion in terms of time and K. We know what time is. Time is 55 minutes. We went from 0 to 55 minutes. So that's where T is. K is going to be our unknown. And what we did was we put everything on this side, and notice when we moved this one, kept this one over here, and we moved this one over there, then log A minus log A0, you have to know how to resolve logs. So when you combine these two values, log A minus log A0 is the same thing as saying log A divided by A0. Right? If you didn't know that, then that transformation, then you'd be stuck. But now, how do you resolve this one? Well, you have to think about what's the definition of a log. So the log of, let's say, x equals y. So what does that mean? That means there's a base here. In this case, it's e. And x then is equal to e to the y. So if this is log x here, there, that's x, then this is going to be equal e to that. So it's e to this power. Okay. So that's where that transformation comes from. It's just the definition of a log. Now we've got that ratio, right? We've already done this part. 35% complete means 65% of A0 still exists as A. Right? So at this point, we say that the ratio between A and A0 is 0.65. That's what this is right here. Now we can set that equal to e to the minus k times 55 minutes, and then solve for k. 7.8 times 10 to the minus 30. Reciprocal minutes. All right. So now we can look at second order. Second order requires a different transformation to get a straight line. We use the reciprocal. So if you say the reciprocal of A and set that equal to, it's actually positive KT plus 1 over the reciprocal of A. 0. Right. So if you want to determine whether your data set is zero order, first order, second order, set up a table. And this works pretty well with Excel. If you're familiar with Excel, if you know how to work Excel, then you can put your data set here, time versus concentration. And then you take the concentration column and set up another column that transforms these values into logs. Okay. Then you set up another column that takes these values and takes the reciprocal of them. Right? So you've got time. You got time, and then you got concentration of A, then you got the log of concentration of A, and then you got the reciprocal of concentration of A. Right? There. You got these values here, you got these values here, and each one of these is transformed there or there. And if you set those up like that, and also if you do it in Excel, you can tell Excel to plot these for you and see very quickly which one is a straight line, right? If this one plots a curve and that one plots a curve and this one plots a straight line, you know you got second order. So this would look, well, this is what the log for this reaction would be still curved, right? So it's not first order. And it's obviously not zero order either. But the reciprocal transformation gives you a positive slope. And remember, when you're graphing these things, these values are actually the reciprocals of that value. So if you want to find out what that value is at any time t, you go up here like at 400 or 4,000 seconds. You go up here like that, you go across here like that, say 350. That's not the answer, because 350 is equal to the reciprocal of the concentration. You got to take the reciprocal of it to find out what the concentration is at that time. Okay. So the slope of this line is, let's see, let me be consistent here. 5 and 1 over A. So we're going to have that, and the slope is equal to K. All right, how about the half-life? The half-life for second order is 1 over K times the initial concentration. Now, just because this says K0 doesn't mean that you have to start at time 0. You pick the time, and then you pick the time, and then you move till you have half of that concentration. How long does that take? See what I mean? You can start at 0 if it's convenient. But say you'd rather move down to maybe 5 minutes, and then you want to go to when it's half concentration from that point. It's just as valid to do it that way. And the half-life actually does depend upon the initial concentration, wherever you start. All right. So you notice anything in common with these half-lives? They're all inversely proportional to K. K's in the denominator here, here, and here. Okay. They vary, of course, the absolute half-life, but they're all inversely proportional to K, right? If K gets bigger, T1 half gets smaller in every case. All right. So let's say, well, let's see. I'm going to have to erase some stuff here, unfortunately. Might as well do it. Painful as it is. Maybe I can just do the first one. All right, so what if we have A yields products? The initial concentration of A is 5 molar, and the first two half-lives are 25 and 50 minutes. All right, let's see what we got. I like to put it in a table. Extract information from word problems and put it on your paper in a form that's recognizable. So concentration of A, let's see. Let's put time first. And the concentration of A here. Right? So at 0 time, you start off with 5 molar. Okay? The first two half-lives are 25 and 50 minutes. So after 25 minutes, how much of this do you have left? Half of that, 2.5. Right, and then the second half-life starts, this is the A0 now, and we're going another, and the first two half-lives are 25 and 50. So what's the absolute time from 0? 50 plus 25 is 75, correct? Right, so this half-life is 25, and this half-life is 50. So at this half-life, you're going to have half of that, 1.25 molar. Okay? Now, that's all the information that we're given. So let's solve this problem. Notice that this cannot be first order, because this half-life is different than this half-life, 25, 50. Those are two different half-lives. And first order does not depend on concentration. So that eliminates a third of the problem right there. So it's a choice between 0 and second order. Does everybody get that? We can eliminate this one simply because it's not dependent upon concentration. Whereas these two half-lives do depend on concentration. Right? The first one is 25 minutes, but now the concentration for the next one is 2.5, and it's a different value. So that means it does depend upon concentration. So now we're looking at 0 order or second order as a possibility. If the rate law were 0 order, then we have the initial concentration divided by 2K. So we can use that. Remember, K is a constant. K should be the same here when we do the two calculations. If we do half-life here for 0 order, then the first one would be half-life equals 25, right? And that equals to the initial concentration, or 5, divided by 2 times K. Okay? The second one would be 50 is equal to 2.5 divided by 2K. And you solve for K. So what would K be here? Well, let's see. 2 times 25 is 50. And then bring 50 over here, put K over there. So 5 divided by 50 is 1/10. Right? Oh, excuse me, that's not right. K would be equal to 0.1. How about this one? Right. If we bring K over here, and then put 50 over here, 2 times 50 is 100. 100 divided into 2.5 means K is equal to 0.025. Right? So it cannot be 0 order because it's got 2 different K values. Right? So you can go ahead and do the calculation for second order just to prove that it's right. But if you're choosing between these 3 and you've eliminated 2 of them, then the third one has to be it. And especially if you're in the middle of an exam, right? You want to minimize time spent on each problem. But this solution does give you exactly the same value for K if we use second order half-lives. And then 1/125th is equal to 8 times 10 to the minus third. So K is 8 times 10 to the minus third. And then the rate law would be Here we go. The rate law would be this K, put that value right here, stick it right there. The rate is equal to this rate constant times the concentration of A squared. That's the rate law. All right. Let's see how I'm doing on time here. Okay, 45 minutes. Okay. So if we use the information from our previous example, can we calculate the concentration of A at time 5:25 minutes? Well, we know what K is. We know it's second order. So the second order is going to be reciprocal, right? So we plug in K, and the initial rate we assume is 5. Right? So after 525 minutes, you have to assume that you start from time 0 for this one. So that means the change in time is 525 minutes. There's your K, and your starting concentration is 5. Then you just solve for A, and you get 0.23 molar after 525 minutes. Okay, so there's all your answer together. So just a reminder, how can you tell the difference between 0, first, and second order laws from their graphs? Let's see. Oh, next slide. Okay. Now, there should be more information in here. Summary of rate. Okay, I'm missing some information. No, I'm not. It's not there. All right. So this is just a reminder. How can you tell the difference? Well, if you plot the raw data and it's a straight line, then you know it's 0 order. If you plot the natural log of concentration versus time, and it's a straight line, it's first order. If you plot the reciprocal of concentration versus time, and it's a straight line, that's second order. If you plot them all together, if you do the transformation on the same data set, plot them all together, if it's second order, then 0 and first are going to be curves. Or if it's first order, 0 is going to be a curve, first order is going to be straight, second order is going to be a curve. So you look for the straight line with those 3 transformations, actually 2 transformations and the raw data. All right, so I mentioned this earlier, so we don't have to spend a whole lot of time on it, but this is, you have it black and white. What do you do if the rate equation is dependent on the concentration of 2 reactants? Like this. In this case, we're going to increase the concentration of B to such a high concentration that it does not change during the initial reaction. In other words, B is constant. And if B is a constant, then we can incorporate B with K into a new constant. So do I have that already in the slide? Let me see. Yeah. Okay. So if B is such a high concentration that it's virtually constant during the initial rate, then we can say B to its power times K is a new constant. We call it K prime. So now the rate is K prime times A to the N. Now we can conduct the experiment and plot the data, the transformations, the raw data, natural log, 1 over and reciprocal, and see which one gives you the power of N. And then you do the experiment again. At a different concentration of B. Let's see. Oh, I've got that. Okay. This discussion is more complete in the lab itself. So we'll, I'll make a copy of that stuff, and the lab exercise itself shouldn't take very long. And then we can talk a little bit about Kinetics lab, which, see, we're not going to meet next week, right? Because that's holiday. Okay. So we'll need to talk about this before you leave today so that you'll be ready when you get back. Or actually, I've got the video on Blackboard for the COVID times. So the whole discussion is there in the video, in case we run out of time today. All right, so this just puts everything together, just like I had on the board. We won't labor that point anymore. Let's see, do we have time to do this? Well, let's see, what does it say? If the initial concentration of A is 5 molar and the K is given, calculate A after 30 seconds have passed, assuming the reaction is. Okay, so we're actually doing a comparison here. If these values are identified for 0 order, it'll give you one value after 30 seconds. First order give you another value, second order give you a different value. So that's what the calculation is here for. Right? This would be 0 order. So there's your K, there's the time, there's the initial concentration. So after 30 seconds, A would be 4.7 molar from 5, right? It's decreased by a little bit. If it's first order, then we plug in those same values in this log transformation, and then we get log of A equals 1.309. How do you resolve that to A? The anti-log of this value is on your calculator. It should say reciprocal of E or inverse of E, 1 over E would be the key that you punch. Let me see what mine says. No, I'm sorry, it doesn't say reciprocal. The common log says log, and above it says 10 to the X. The natural log says E to the X. So you punch in this number and then punch E to the X, and that will give you this value. So notice first order kinetics are faster than 0 order. You end up with less, 3.7 instead of 4.7. And as you may guess, second order is going to give you even less. But you need to use the correct equation. Right? And you end up with 2 molar if it's second order. So I think the whole point of this slide is, depending on the order of the reaction, first order is faster than 0 order, and second order is faster than first order. Moral of that story. Now let's look at the method of initial rates. So here we have lots of information. I mean, it can swamp your brain if we don't pick it apart. So this is the reaction that we're investigating. The manganate ion. This one is oxalic acid, probably. This is extra acid. Right? And the yield, the manganese 2+ ion, carbon dioxide gas, and water. Okay, so the initial rates are in terms of the reactants. Right? When a problem says initial rate, it's always in terms of the reactants, because we're starting at the very beginning. There's no products, so you can only describe the reaction in terms of the reactants. So we've chosen this concentration for the manganate ion for this experiment. See, initial concentrations. This one for manganate, this one for oxalic acid, and this one for additional acid. 1 molar, 10 to the minus third molar, 10 to the minus third molar. And we get this rate, molarity per second. Let's see. Now that's going to incorporate, the reason it doesn't say molarity of what? It doesn't say which component, because it actually combines these 3 components in the rate law, right? It's going to look like this. Rate, the differential rate law, is going to be some K value, and then MNO, let's make that bigger. Right? This is going to be some value there. It's order with respect to MnO4 minus. And then this one is going to be the oxalic acid. This is going to be N. Then this one's going to be hydrogen ions. And it's going to be Mn, you know, what did I use? P. We're not going to use O because it can too easily get confused with initials. So and it's called P. So each one of these is going to have a different order. And if the rate is in terms of molarity per second, it has to incorporate all of these together. That's why we don't say initial rate of what. It's initial rate for the reaction. Okay, so we've got 4 separate experiments. This one gives you that rate. Now we've increased the concentration of MnO4, initial concentration, to this, but these 2 remain as they were. This one is the same as it was here, but now this one is held constant and this one changes. And then for this one, we hold this one constant, that one unchanged, I shouldn't say constant, unchanged from this experiment to this one, and now we let this one change. So the key here is you hold these constant and let one of them change. So you compare this reaction to that reaction to find out information about that one, because this is the only one that changed. Or if you compare this one to that one, which one changed? This one changed. Now we can find out information about the oxalic acid. And from this one to this one, we let this one change. And now we can find out information about that one. That's the structure for design structure for initial rate reactions. You always hold unchanged and let one of them vary. And if you have the right mix, then you can get information here. It took 4 experiments to get information on 3 components. If you only have 2 components, then it may only take 3 experiments. All right, so that's the structure of our data. Now what do you do with it? Let's see. Is it going to make me do that on the board? Yeah, I guess it is. Okay. So we'll take 1 as an example. Right? With this as our guide, and K is going to be unknown. What's the rate for this one? 2 times 10 to the minus 4, correct? 2 times 10 to the minus 4 equals what? K. And then this one is 1 times 10 to the minus 3, the M. And this one is 1 times 10 to the minus 3, to the N. and this one is 1 to the p. Okay? That's one rate law. Now we're going to write one for this one, which changed. Right there. And its rate is 8 times 10 to the minus 4. 8 times 10 to the minus 4 equals the same K, right? This reaction has one K and one K only. So what's this one? This one changed to 2 times 10 to the minus 3 to the m power. This one didn't change. And this one didn't change. Okay? Now what we're going to do is ratio. Just divide one by the other. Actually, it would have been better if I could have ratioed, put this one on top. Let's do that. So we're going to put the second one on top, and the reason should be obvious. 2, yeah, 2. And this one is 8 is 2, and this is 1. So now if we divide one by the other, what do you get? This one cancels. This one cancels. And this one becomes what? 4. That divided into that is 4. The reason I did that, of course, was to give me a whole number here rather than 1/4 reaction. And then this one is K divided by K. Well, actually, that's 1, right? Yeah, that's 1. We're looking for first input part, first bit of information you get from this type of manipulation is the order. Right? So what do we get here? Well, this number divided by this number, and they're both to the same power. So you should get 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3 to the m power. Everybody see that? That's mathematical. That's legal. So this divided by that is 2 to the m is equal to 4. So what could m be? It has to be 2, right? 2 squared equals 4. So m equals 2. Now you can put 2 here. Okay? And you do that same thing for the other 2. Like you compare this one to this one, and that gives you a comparison of this one, and ratios these two, and you end up with the same situation. You say, what could n be? And then you do the same thing for these two, and then you find out what could p be. And once you find out what they are, as it turns out, we do that whole thing again. This is 1 and this is 0. And then once you've got these orders, then you can take any one of these, plug in the concentrations with their orders, the rate. Let's just take the first one. You put the rate here, put the concentrations here with their orders, and solve for K. And that's where we get this value right here, 2 times 10 to the 5th. Okay. So that's the general, actually, those are the steps in solving an initial rates problem. I know it takes time, but I didn't make this stuff up. I'm just the messenger. Okay. Now that you know the rate law for any reaction, we want to use that information to try to tease out mechanisms. What's actually going on in that arrow between reactants and products? And it usually, rarely occurs in one step. It's usually 2 steps, sometimes 3 or even 4 steps. So what happens? Well, these elementary steps, right? The sequence of steps, you know, this happens and then this follows it. And then this follows that. They occur in order. And once you propose your elementary steps, one of the rules is conditions. You have to be able to add those elementary steps up to the overall equation. That's the first rule. If you can't add up your steps to the overall reaction, then that mechanism is bogus. It's out. And that's usually what happens. You use your experience as a chemist and you propose mechanisms. You say this. That's one proposition. Then you do another one. Then you do, sometimes there'll be dozens of proposals for a reaction. And then you start eliminating the ones that are obviously wrong. And try to narrow it down to 2 or maybe 3. All right. So here's what a possible mechanism, actually this mechanism, elementary steps, was determined, has been proven for this reaction. So NO2 plus carbon monoxide yields nitrogen monoxide and carbon dioxide. So step 1 is we take 2 of these, which is, this is N, this is O. So this NO2 and NO2 takes 2 of them together. Notice that there's only 1 in the overall reaction. So how do you end up with 2 here? Well, we'll show you. 2 of those together yields NO3 plus NO. And then you take this NO3 over here and you react it with carbon monoxide. And that gives you the NO2 plus carbon dioxide. So notice when you add these together, that one cancels out this one because they're on opposite sides of the arrow. Okay. So it meets the first condition. When you add these 2 together, you get that overall reaction. Now, a word about these elementary steps. And the official term is molecularity. Molecularity just means how many molecules come together in an elementary step for the reaction to occur. If we go back, molecularity here in this step is 2, right? It's bimolecular. These 2 come together. This is bimolecular. These 2 come together. Okay. Unimolecular means only 1 molecule is involved. So it just breaks apart or does some sort of reaction. And it's always first order. Now we can say something about the order of the reaction with respect to the elementary step. So unimoleculars are always first order reactions. Bimolecular, where you have 2 come together, 2 reactants collide, that's second order. Termolecular, where you have 3 come together, is third order. We didn't talk about third order. And one of the reasons is it's very rare. Think about what has to happen for a reaction to occur. Okay? You need 2 things. You need energy. There has to be enough energy to exceed the required kinetic energy for that reaction. And they have to be oriented correctly. So if they need to come together like that to react, but they come together like this, it doesn't matter how much energy they have, they won't react. So there's a limitation here on bimoleculars in that, right, relative to that orientation and energy. Just think about it, if you've got 3 molecules that have to come together in a certain energy and orientation, it's almost impossible to get them to do that. So most mechanisms avoid proposing termolecular steps unless absolutely necessary. There's no other way to explain the reaction, then we'll go to termolecular. They're very rare. Elementary steps. Okay, once you've got the mechanism, or actually 2 or more proposed mechanisms, you can look at them in terms of which one is the slowest. The slowest step in a proposed mechanism, the slowest elementary step in a proposed mechanism is the rate determining step, right? Nothing gets by that step at a faster speed than it can go. So the overall rate of the reaction is determined by the rate limiting step, the rate determining step. And there it is. A reaction is only as fast as its slowest step. You've heard this expression, a chain is only as strong as its weakest link. Same concept. So while the overall rate law can't be derived from the balanced equation, elementary balanced equations can be used to derive overall rate laws. So that's another condition for the proposed elementary steps, the mechanism. If you can derive the overall rate law from a combination of the elementary steps, then that's another feather in your cap. That's another point saying that your mechanism is probably true. Okay. Okay, that's fine. I didn't want to flip slides until you were done. Okay, so here's the summation of what I just said. The sum of the elementary steps must equal the overall balanced equation. That's conditional. And then the mechanism that is derived from these elementary steps must agree with the experimentally determined rate law. Those two are absolutely sacred. You cannot violate those two. All right, let's see how I'm doing on time. I'm about to run out. Yeah, I'm going to run out of time. Let's see, do we need to stop for this? Decomposition of N2O5. So what are the proposed steps? Well, in this one, we're saying N2O5 breaks down into NO2 and NO3. Notice, NO3 is nowhere in this reaction. So NO3 is an intermediate that enters into the next step. So NO3 plus NO2 gives you NO02 and another NO2. Well, actually, this NO2 is the same as that one over there, and this one breaks apart. And then you take the NO3, another NO3 here, and you react it with the NO to give you two NO2s. So the NO2s are good. You've got an NO2 here, you got an NO2 there, so you got four of them. You've got an oxygen, so that's good. Now, do the others, how many of these do you have? Well, you've only got one in the mechanism, so what do you have to do? You've got to multiply it by 2. So in that case, now you've got N2O5, 2 of them. You've got 2 NO2s, and you've got 2 NO2s here, so that's 4 NO2s, and this NO2 cancels that NO2. So far we've satisfied. Now we've got O2. How about NO3s? You got 2 NO3s here, and 1 there, and 1 there. They cancel, so we're good. All right, that satisfies the first condition. Okay, example. Let's say we have this reaction. Some chemical A plus 2 B's yields C. And we propose this mechanism. A plus 1 of the B's yields D, and then the D combines with the other B to make C. And we're saying that this one is the slow reaction. Right? This one is the fast equilibrium, which means we haven't even discussed equilibrium yet. But what it means is it goes backwards and forwards really fast. So the only way that this one can proceed is if D is used up. So as D is formed, it's used up in this one, but this one occurs slow. So this goes backwards and forwards, and occasionally one of these D's enters the slow step. And eventually, at this rate, not at that rate, but at this rate, determines the overall. Does it meet the first condition? Let's see. One A, two B's, a C, and D's cancel. Yes, it does meet the first condition. Yeah. Okay. So when you've got a situation like this with the elementary steps, we say there's a rate constant for this direction, and then there's a rate constant for the reverse, and then there's a rate constant for this one. So this one is K1, this one is K minus 1, because it goes the opposite direction. And this one's K2. K2 is the rate determining. Right. So there's the slow step. And based upon this, the rate for K2, remember in this case, for mechanism steps, we can use the balanced equation. So there's one of these, remember, this is overall bimolecular. So the overall is 1 for D and 1 for B. So that's the overall order is 2, bimolecular. Right, so 1 for D and 1 for B. And then the K2 for that reaction. But notice when we write it this way, that there's nothing here. No, there's no D up there. So that can't be the final answer. We got to do something with that D. Right? D is not a reactant, so we got to get rid of it. Right? So we go back to the steps and we say the fast step, excuse me. Here we go. There. What we're going to say is I think I skipped a step. Yeah, I think I skipped a step for that explanation. Yeah, I did. Let me go back. There we go. So K1 is A to the first to B to the first, right? Bimolecular, 1 for each one, is equal to the same, since it's a fast equilibrium, that means the forward rate is equal to the reverse rate. So that's the rate of the forward reaction is this, and the rate of the reverse reaction is this. You see that? No? Okay. Remember, take this one times that one times the K, and that's the rate for this direction. You go in the reverse direction, you have the concentration of this one times the K value for that reaction. But it's an equilibrium. They're equal rates backwards and forwards. So this one is equal to that. Okay. Now we can solve for D. So we solve for D and we get this expression. There we go. So that's where that one comes from. We're going to substitute that in this one. Right? We said K2 equals D times B. So now we've got D equal to this. We substitute that in there and we solve. So now we get K times A times B to the second power. Right? And this K is equal to that K2 times this K1 divided by that K minus 1. So this is the rate law for that reaction. Yeah, I got 10 minutes before we have to go in the lab. Yeah, what?
I was gonna say, don't you have the lab recorded on YouTube from last semester?
Yeah, right. Instead of doing the lab, just Just watch it and fill out the.
Finish our lecture and then we could just watch it and fill it out, unless you want to do that.
Does it want to go out?
No, I'm saying. if
Well,
you-
the lab, we have two choices. You can actually physically go in the lab and perform it. Or you can watch the video where I do the lab and show you all the steps and generate the data. And then you
It'd
write
probably be
them.
more helpful if we do it, what do you think?
I think
Yeah,
so
I
too.
mean, that's fine.
If we
I'm just
can.
saying.
Let me try to finish this. Okay, the collision model for chemical kinetics requires what? First, molecules must collide. They've got to come in contact with each other in order for a reaction to go. And the main factors that influence that reaction upon collision are activation energy. They need a certain amount of energy. If they don't have that minimum amount, then the reaction will not happen. And that is largely dependent upon temperature. Right? So if you have higher temperature, you have higher kinetic energy. Right? Temperature is the average kinetic energy of the molecules in a mixture. And then you have the orientation. So I mentioned that, actually I mentioned both of these before. That's the collision model for reaction. So how do we determine activation energy? Right. Well, first we need a concept. So if this is the progress of the reaction, here we got reactants starting, and here we have products ending. And we know from first semester about endothermic and exothermic reactions. Right? So exothermic reactions means that the products have less energy than the reactants. They give up that energy during the reaction. And this is what it looks like during the reaction. You have the reactants here, and you need some energy. You got to boost the energy up to this point to a transition state. And then if there's just a hair more than activation energy, you'll go over the hump and the reaction will complete. And the products are down here. In this case, if the product energy is less than the reactant energy, that's exothermic. They give off energy. But that's the activation energy required. The difference between here and that activated state. Okay. Let's see. This is a Rhenius equation, and it's useful, but there are other versions of it. What it does is it takes into account some various proportionality constants here, and of course this one you recognize as the gas constant R. This temperature is always in Kelvin, and there's the activation energy. So if we know the K for the reaction, and we know the temperature at which it occurs, we can calculate the activation energy. Except we don't know what this is. That varies for reactions. So we need another form to make it useful. And this is a form that you may recognize this as a straight line, right? There's Y, there's X, there's the slope, and there's the y-intercept. So if you plot on the x-axis 1/t, you do several experiments at different temperatures. And you take the temperature and plot it against the K value that you've determined at that temperature. Right? The K will change with temperature. And then you take the natural log of K and plot these two, then the slope of that line will be minus activation energy divided by R. Right? This is what it would look like. So the slope of this line is equal to log K over 1/t. Here's K. Let's see, there must be more to this. Hold on a second. No, there's not. This value here would be, you could set that equal to, back up, to this right here. Right? Plug in your R value, and that R value is the one with joules, not with liter atmospheres. That's 8.23 something. and set that value that you determined from the slope equal to this, R is a constant, you can solve for activation energy. Okay. All right, we're not gonna do this one. You can look at this one. This says this is basis upon the rule of thumb in chemistry is for every 10 degrees increase in temperature, the rate doubles. So I asked the question, if we go from 25 to 35 degrees, that's a 10-degree increase. What would the activation energy have to be to actually meet that condition, right? If it's just a rule of thumb, it could be like a wide variation. So I just run through this equation and we end up with the activation energy would have to be exactly 52.9 kilojoules per mole in order for the rule of thumb to be accurate. Okay, what's a catalyst? Catalyst is anything that enters a reaction one end and comes out the other. In the mechanisms, it participates in the reaction, but it's reconstituted and spits out the other side. So overall, the catalyst looks like it went in and is unchanged. But what a catalyst does is it speeds up the reaction. How does it speed up the reaction? That's the key. With a catalyst, the activation energy is decreased. Right? So now, at a given temperature, the molecules have enough energy to cross that hump. More of them can cross that hump than could at this higher activation energy. It provides an alternate pathway at lower activation energy. So the activation energy for this pathway will be different than it is for that one. But the reaction itself overall is the same output of energy. It's the same exothermic or endothermic output. It's just, it goes faster because the catalyst gives it an alternate pathway. It's another way of looking at it, right? If this is a spread of energy for all molecules in your mixture, then uncatalyzed says these are the only ones that have enough energy. Right? The total number of molecules is the area underneath that curve. So these only have sufficient energy uncatalyzed. Whereas if you catalyze it, that makes more of them with sufficient energy. Okay, heterogeneous catalyst. You have different phases. Reactants and catalysts are different phases. So if you have gas going through your tailpipe and it crosses over ceramic beads that are covered by platinum and let's see, one other. Let's see, platinum and palladium usually. That's a catalyst, but it's in a solid phase. So that's a heterogeneous catalyst. It's in a different phase than the reactants. Let's see. So there's your catalytic converter. I think now the matrix is solid, right? Initially, catalytic converters back in the late 70s, they started using them, actually the middle 70s. Mechanics soon found out, shade tree mechanics soon found out all you need is a screwdriver, poke a hole in the bottom, and all the ceramic beads would flow out. So then you patch the hole, and you got all the engine power is back. Right? Catalysts rob your engine of power because of the back pressure. So they figured out, well, maybe we better make that matrix solid and just porous so that they can't poke a hole and get it out. Homogeneous catalyst is one which is in the same phase as the reactants. And a perfect example of that is hydrogen peroxide and potassium iodide. If you've ever seen hydrogen peroxide with put a little soap in it and maybe some coloring, and then you throw some, you dissolve potassium iodide in solution and then dump it in there, then pretty soon it goes, it just makes a big colored smokestack of bubbles. Oh, I do have a video on here. Let's see, is it gonna go?
try yours. So that's the technique. Just dump it right in and see what happens.
Oh, wow. Okay.
Okay, so
Whoa.
we're releasing
okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped by the soap, okay? It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff. This is like more of
As a matter of fact, hydrogen peroxide works on wounds because most pathogenic microorganisms don't like oxygen. They prefer anaerobic conditions, especially the ones that cause gangrene and Clostridium. So if you can make a lot of oxygen, whenever you break a cell, it releases a universal catalyst that all cells have called catalase. And they're inside the cell, and their purpose is to break down peroxides that are formed by chemical reactions inside the cell because they could damage the nuclear material. So this catalase breaks those down before they have a chance to damage the cell. So when you break your cell, that catalase reacts with the hydrogen peroxide and fizzes. In this case, instead of using catalase, we used potassium iodide. And it did the same thing. I had a student at Logan at Southern one summer. His wife was expecting, and they found what the sex was, and they did a reveal party using this. Right, different color.
That's what I was thinking. I was like, dang, I should do that.
Yeah. The problem was they got the sex wrong the first time they had the party.
Oh.
So they had to do it again with a different color. And of course, the student I'm referencing said, that's great. I love doing this stuff. So he did it again. Okay, so this is a proposed mechanism for what we just saw. Right? It's got 4 steps in it. And you notice that the iodide comes in this side, goes down here, down here, down here, and spits it out right here. So it comes in here, it goes out there. That's how you identify the catalyst. It comes in one side, goes out the other side, unchanged. Now, intermediate would be something that forms inside and doesn't come out the other end. But the catalyst starts with the first mechanism. I guess it's possible it could be intermediate, but it comes in, but it goes out unchanged. Let's see, this is one that occurs in the upper atmosphere with ozone. Let's see, in this case, nitrogen monoxide is the catalyst. Comes in this side, goes out that side. Freon does the same thing. That's why a lot of refrigerants are now banned